So guys, this is P4. So as per normal, I'd do my circles. Now I've got my pre-made circles because it's very hard to do that from where I'm sitting. And I would put P4 waves in the center. Anyone know why I put that in the center and make it really obvious? Yeah, it is the topic name, yeah, absolutely. But any other reasons? How many of these pieces of paper are you going to have? 15. There are 15 of them. And they're split into two papers, so it's really handy if you can quickly identify which ones. Now, P4 is part of your first paper. Okay, it'll only be a small part, about 15-20% of it. Okay, so it's manageable. There's not too many formulas in P4, but there's a lot of facts and understanding. Okay, so this is why we're going to be a bit fact heavy in this lesson. So what do we remember from waves? What do we need to know about waves? What do you guys remember? Anything at all? Go on. Okay, there are wave types. Did I put wave types down anywhere on here? We'll put wave types here. And what we'll do is we will put a little arrow out because there's two types we need to know. We've got transversal waves, which is where you were on the right track, and they're typical to things like light. So light moves in a transversal wave. What other kind of waves do we deal with? You can either tell me the name of that wave or a type of it.
Sound wave. Sound
wave. Well done. So hang on, I'll put after transversal, I'm going to put light. Come in. Oh, hello, sir.
Morning, everyone. You've already said morning, haven't we? So, you alright, sir?
Very good, sir. So sound, does anyone remember what type of waves sound are? They are very different in the way they behave. Starts with an L. Anyone? Alright, this is why we do this. Longitudinal. Okay, so I'll write longitudinal in here. So we've already got off to a good start. We've got our longitudinal. Now, spelling is not my forte. I'll be honest about this. Okay, and they're just examples. They're not the only type. Transversal waves, earthquakes have two types. The first wave that reaches you on an earthquake is a longitudinal wave, and the second one is a transverse. Just to keep you guessing. You can guess which one does most of the damage, not the longitudinal. It's the same way as if I wanted to push you over, I wouldn't shout at you. Okay? If I shouted loud enough, you would move a little bit. My sound waves would push you. But if I wanted to make you move, I'd grab hold of this carpet and I'd shake it and make a transversal wave. Okay? And you would, hence why buildings fall over. Okay, so types of waves. Can I throw in wave parts? Okay, so I'm going to put wave parts over here because we do need to know some of the wave parts. Can anyone remember any of the parts of a wave? I'll get you started by drawing one because ideally you should just have the diagram on your revision notes. So I want to know what this part here is, and I want to know what this gap here is. I want to know what this bit is. They're arrows, by the way, in case you're guessing my drawing. Anyone throw out some of the names? What are we talking about? What's the height of the wave? I've turned your music up really loud. Any guitar players who plug their guitars into a amp? Amplitude. Okay, so amplitude is this one over here, and it's the height of the wave, the noise, if you like. How much energy does it have? If I turn up the amplitude on your speakers, the sound is louder. Now that's not even doesn't matter if we're talking longitudinal or transverse here, the amplitude is the amount of energy it has. As I talk louder, I have more amplitude. Right, what's one of these spots on the top called? Anyone remember what a spot on the top of a wave might be called? We have a few names for it, so I don't care if you guess and you're wrong, because I'll steer you. Anyone? What would we call the top of a mountain?
Peak.
Peak, and that's the same one. Same. We sometimes use peak. We can use crest. It doesn't actually matter, and its proper name, not that you actually need to know this in GCSE, is an antinode. I like to include that just in case. Antinodes, okay, and it's all this means the same thing. It's the top of a bit, and at the bottom, we'd also in A level would call that an antinode, but it has another name at GCSE. So what would we call the bottom of a wave, or a bottom of a sea wave? So help. What do horses drink water out of? Any horse people here? No one at all. I didn't invite the horse people in for my first lesson. Did someone say trough? Oh, I thought I heard it. Okay, trough. If you did say it, well done. Be brave. You were right. Okay, so the distance between, and I'll draw in another trough, just so that it doesn't look like I'm cheating here. Hello, come on in. We can have the distance between two peaks, or two troughs, or any two places that are the same point on the wave. We're looking for a particular description of that length. I'm giving you a hint there. What we call that length between 2 points on a wave. Go on. It is wavelength. Well done. And wavelength has a little symbol. It looks a little bit like that, and I'll write it in above. Okay, so we're actually writing a lot more information on here than we want to have at the end. Okay, when we get to this, we just want a picture of this with a couple of dots marked on it so that we can remind ourselves, a bit of recall. Oh, what was that point called? And if you do that enough times, you won't keep looking it up because you'll remember it. Okay, so we've got wavelength, amplitude. Oh, okay. So at this point, I've got a nice stretched out wave. What if I draw the same wave? So it's, and I'll make the amplitude as close to the same as I can. So let's say it's about there and there. So it's about the same as the one above. Now this time round, my waves are much closer together. What could you tell me the difference between these two waves? Anybody? I'll give you a hint. Higher what? Higher what? Frequency. So who said higher, by the way? Well done. You are correct. We just need to tie that together. Higher frequency. So this one here is a higher frequency than the one above it. Okay? And that is an easy 6-mark question where they might be asking you to tell me the difference between these two waves. And you need to point out that they've got the same amplitude. I'm talking in a really high-pitched voice, but I'm not talking any louder than this. But this voice is much deeper, so a lower frequency than this high-pitched voice. Okay, and I can't keep doing this for very much longer. I'll get confused quickly. So that's a key point, higher frequency, the waves are all squished together. They're happening more often. Right, let's go on to wave speed. Now this is probably our big formula for P4. So straight away, I'm going to get you started. Wave speed is velocity equals what times what. I'll give you a hint. They're both on the diagram we've already drawn. Frequency, good. Got us started well there. Frequency, nice big F. Frequency times a what?
Wavelength.
Wavelength, spot on. Okay, so that is our wave speed formula. And our very first task this morning is we're going to find the wavelength of Wi-Fi. I thought I'd make something relevant to you guys. If you've done this with me in class before, you'll know part of the process. So we're going to talk about that Wi-Fi router that's up in the corner of the room. You'll have to believe me if you're watching this online. And I'll give you some of the information about that Wi-Fi router. It has a frequency of about 2.48 gigahertz. Don't panic, I'll go through giga in a second. Its velocity, can anyone tell me how fast the waves come out of, what kind of waves are coming out of that Wi-Fi router? I don't care if you're wrong, throw up some guesses. Are they sound waves? Can you hear it? What's the other kind of wave that we deal with a lot? I can see you all. Why can I see you all? What kind of waves? Why can I see you guys?
Light.
Light. Yeah, that's all I was looking for. What the problem with the misconception we have here, guys, is people can see the light coming off the board, so they go, "Oh, that's a light wave." What comes out of a Wi-Fi router is a light wave as well. It's just not in the visible light spectrum. It's still a light wave. It's just not a light wave you can see. You can stare at that Wi-Fi router all you like. You'll never see Wi-Fi, but it is there. It's a microwave. It's the same kind of frequency that your microwave oven uses. So, how fast does light travel? There's my follow-up question. Anyone remember the number? You don't have to know it for GCSE, but it's just handy to know what it looks like. Anyone? Right, I'll throw it out there for you. 3 times 10 to the power of 8. And what are all velocities in physics? We did this with P1 last week. Anyone remember? What unit would we have for the speed? Meters per second. Is he right? You don't look confident, Harvey. Come on, back him. Is he right or wrong?
Right.
You're going to go right because you don't know any better?
Yeah.
Good answer. Why not? Anyone got anything different? I hope not, because meters per second is spot on. Okay, so far we've got 2 units appeared here. Hertz, capital H, little z. Very common question for 1 mark. What is the unit for frequency? Hertz, capital H, little z. Easiest mark you'll ever get. Meters per second is our other unit here. So straight away we need to find our wavelength in this equation. So I'm going to rearrange it. So velocity equals frequency times wavelength. I want to know wavelength on its own. So I'm going to do wavelength here. Velocity divided by frequency equals that. So on your calculator, guys, you've got 2 numbers to put in, but before you get there, there's a couple of things we need to do. Because if we put in 2.8 for frequency, we're going to have a very strange answer. We need to put in something that represents giga. Now, on the side here, I'm going to write this down the side. We're going to have giga. Go on, I'm listening.
When you put the equation for it below 3 times 10 to the power of 8,
Yep.
say velocity equals velocity times.
Oh, velocity equals. Before I rearrange equation, I'll always write down the equation I'm about to rearrange, just in case I make a mistake, because then the markers will always award marks for mistakes carried forward. All right. Okay, so giga, mega. Now you see I'm putting all these down the side. Kilo. So some of these you're used to. Kilogram. How many grams are there in a kilogram? 1,000. There's a lot of people not looking so sure. They must be buying a lot of sweets when they accidentally ask for 15 kilograms of sweets. Must be an accident. Okay, so kilogram is 1,000. 1,000 looks like times 10 to the power of 3. Now I'll help you out with mega. Mega is 1,000,000, and that's times 10 to the power of 6. See a pattern starting to appear here? Times 10 to the power of 3, times 10 to the power of 6. What do you reckon giga might be? All close, not double, another 3. 9. It's alright, it was a good guess though. I would have originally respected the guessing. 3, 6, 9. Nice and easy. So we're actually going to replace the giga that I've got down here drawn with an arrow with times 10 to the power of 9. That's the number we're going to put into our calculator. Just before we do that, I'm going to go the other way because I think it's always useful. How many millimeters are there in a meter? Anyone? How many millimeters are there in a meter? How many millimeters are there in a centimeter? 10. How many centimeters are there in a meter? 100. So 10 times 100 is? 1,000. That's how you get there. There are 1,000 millimeters in a meter. So millimeter is times 10 to the minus 3. Now you're going to see that pattern appear very similar again. What do you reckon micro might be? Times 10 to the minus 6. Nano times 10 to the minus 9. There you go, guys. That's all you need to know for GCSE in terms of our prefixes. Okay, so giga, mega, kilo, these are all prefixes. These are ways of simplifying very big numbers. Because if I walked around saying, could you pass me the Wi-Fi router that's 2.48 times 10 to the 9 hertz, please? It's going to start hurting. Yes?
Under the times 10 to the power of minus 3.
Yep.
The word.
Oh, micro. Sorry, I'm drawing on the line. We've got milli, micro, then nano. Okay? Now, an easy way of remembering it, if you ever get confused going down, is nano starts with N, which is also the first letter in 9. Okay, nano for 9. Useful. Okay, so in our calculators, we want to get this out. We want to use this button here on our calculators. Okay, that button, the fraction button if you like. And then we're going to put in 3 times 10 to the power of 8. And then we're going to put in our frequency, which is 2.48 times 10, don't forget this bit, times 10 to the power of 9. and then hopefully someone will be able to give me an answer at what unit do we use in physics for distance. What's this going to be in? I'll let you put in your calculator. If you're doing this at home, put it in your calculator. We're all busy beavering away here. Anyone got an answer yet? It does take some time. Try and get it all in your calculator in one go. It stops a lot of mistakes.
The fraction or
Do it as decimal.
okay, 0.12.
0.12. What unit do you reckon that might be in?
Was it the distance?
Well, there's distance, yeah.
Um,
What unit do we use in physics for distance? You are right. Well done. Did you hear him? If you didn't hear him, meters. So if you've got 0. Has anyone got anything other than 0.12? Please make sure you get 0.12. If you can do this calculation in your calculator, you won't find much more difficult in physics to put into a calculator. Okay, there's a few traps here to go. Okay, so hopefully at home as well as in the classroom, and I'll put another equal sign down here, we've got 0.12, and because it's a distance, in physics, meters. That means that the wavelength of Wi-Fi is about 12 centimeters, or 0.12 meters. About that. Every wave that comes out of that box is about that size. It would look like that if you could see them going around the classroom. In fact, if we took that out into the field, I could actually get you to stand with your phone and you could move it up and down the wave. And if you're at the point, this point of the wave, and I'll draw an arrow on the board so those at home can have some idea what I'm talking about. This point here, which is the node, at this point there's no energy transfer. So if you put your mobile phone at exactly that point of the wave, no Wi-Fi. Move it 6 centimeters further along, because then you're at the other half of the wave, or quarter wave I should say. So what's a quarter of 12? Quarter of 12? 3. 3 centimeters later we'd move up to the peak, and then you'd have maximum Wi-Fi signal. And you'd have no signal, signal, no signal, signal. Now the reason that doesn't happen in your home is because that Wi-Fi wave comes out and bounces all over the room. So there's lots of different parts of that wave reaching you all at different times. Okay, and that's one of the things that makes Wi-Fi work well. But that's a good example of finding something from that wave speed formula. Right. Let's move on to, let's do one of the practicals. Now you might have done this when you're a bit younger. And I'll do it this way. Oh, that's meant to be a C. Clapping. So you go out into the field and you're clapping. Now there's two things that are going to reach you when you watch someone clapping from the other side of the field. What are the two things that you're going to... Sound, so you're going to hear, fine. So I'll do it this way around, sound. What else is going to reach you? Speak up. Light. Okay, what are you going to see with light? What would you see if someone was clapping on the other side of the field? You'd see them, you know, raising their arms, and you'd be able to clearly see that, right? What's the difference between the sound and light? Other than the fact they're different types of waves.
Light travels faster.
Light does travel faster. We've already just said how fast light travels. It's quite fast. 3 times 10 to the power of 8 meters per second. You want to know how fast sound travels? Roughly. Any guesses?
200 miles an hour.
Yeah.
No, 500.
It's actually a little bit faster than that. Yeah, it's quick because we can't tell, can we? Because when I'm talking to you now and you're talking back to me, it looks like it's like instantaneous, and it's not far off. Okay. The figure that we typically use is 342 meters per second. So it's still quick. So if you're at the other end of the sports field, it only takes a second for the sound to reach you. But of course, they're clapping, aren't they? And you see the clap, and then you hear it. Okay, so you can see, it's like shouting across, if you go into mountains and hearing the echo. It takes time for sound to travel. Okay. The next one I'm going to move on to is refraction. So I'm working my way around the table here, circle, and who wants to tell me a little bit about refraction or refractive index, more particularly? Anyone remember now we do cover a bit of refraction in P5 as well, so I won't go into too much detail. Anyone remember the experiment you did with refraction? Anyone have a clue what I'm talking about? Is there any refraction going on in this room right now? There might be a tiny bit. Anyone got diamond earrings in? Anyone? Yeah?
Is it when something like goes up and then bounces back?
That's reflection. Close. No, it's in the same ballpark. Light is doing something, it's changing path, but it's changing path in a slightly different way.
Isn't it where it goes through like the glass block and it like bends a bit?
Okay, bends a bit. We'll work on that, but yes, you're spot on. So we're talking about when light passes through a glass block. So you probably had a light box. So I'll tell you what, I'll draw a little picture of it. So you probably had a light box, and you probably had light coming out, and it hit a glass block. Change direction. I will change color here because otherwise this gets very confusing very fast. It changed direction. Does that look like a change direction? Phew. Come on, pen, give it back. I hate when this happens. Bear with. Right, there we go. And then we change direction back to where it was in the first place. So these two are parallel with each other, okay? And that's our glass block experiment. So what's occurred in here is refraction. However, if you're paying attention, there would have been some reflection going on as well. So the reflection would actually have come off this way. And we would have got you to draw on a piece of paper and with pencil draw around it, mark where the light was coming in, where the light was coming out. And then we got you to pack up, and then we got you to try and get a protractor out, and then it all went wrong. Always goes wrong the first time you try this, but that's okay. Because what was the next thing I would have got you to draw in? It's really important. Where the light hits the glass block. We need to draw something really important in. It's 90 degrees to the surface. Does that help anyone? You use this in maths a lot. And you draw something 90 degrees, something else. It's called a normal, okay? So I will draw it in, I'll switch to green because I think this is now getting a little on the small side. And we would draw, if I can find my pen, there we go, our normal 90 degrees, and I'll draw 90 degrees to make it really obvious, and that is our normal. And that's our normal that we measure everything from. So this angle in here is measured between the normal and the light, and that's our angle of incidence, and I'll put a little eye there for you. This angle in here, okay, so the little one is the angle of refraction. I'll do an R for it. Now I know we're getting a bit small there, so remember you can always look up your class notes. You should find this practical in your books. You'll also find about 1,000 YouTube videos on it if you feel so obliged to watch someone draw lines around a glass block. We take those two angles. So we've done all the practical work here, and the angle of refraction, or the refractive index, which is actually more useful to us, and I'll just do Ri for refractive index equals sine angle of I divided by sine angle of R. Now before you panic, your calculator does all this for you, okay? You literally put it into your calculator exactly how it looks. So I'll give you an example of one. Let's imagine we have an angle of incidence. So I'll put it, where can I hide it? Here we go. Angle of incidence that equals 42 degrees. And we've got an angle of refraction that equals 12 degrees. Put it in your calculator exactly like that on the right hand side. Have a go at it. So you need to use the fraction button first. So press the fraction button. So fraction button, I'm doing this down the bottom with you. And then put in sine, and it'll open up a bracket for you. Put in 42 for the top one. And on the bottom line, press sine again and put in 12. Let me know when you got an answer. How you doing, Alex? Got an answer yet? Let me know when you do. Give everyone a chance. half of this is just literally practicing how to use your calculator. So you're not trying to do it in a rush, the real thing. How are we doing back row? Got an answer? Alex? What did you get? Not yet? I'll keep going then. Got one, Harvey? Is it greater than 1? Good. If you get less than 1, you've made a mistake. Alright? A few people just finishing off. If you get syntax error, it's likely you haven't closed brackets, if your calculator is that way inclined. Mine gets very fussy. Any joy? Alex, I'll catch up with you later if you're not quite there. Back row, who wants to offer up a number? Go on. Not working? You alright, miss?
Yeah, just running from the lower ground to the top.
Yeah.
Have we got Amy Cameron? Fabulous. Lovely.
Excellent.
Well done. Thanks so much.
Back row, anyone offer up a number? What did you get? 3.2. Anyone not get 3.2? That's good because that's the refractive index of diamonds. Okay, that's why diamonds, if you shine them in the light, give you that lovely rainbow fleckled patterns because light changes direction massively into a diamond. Okay, it makes them quite unique in that respect. And they've got lots of cut edges as well, which is what gives them their nice characteristics. But anyway, that's that one practiced. Let me switch colors and we will go over to the other side and we will do some bending of light. That's our next one. So where's my mouse gone? My mouse is here. Okay, so I've just called this bending of waves. Okay, and we've got 2 different waves. What are our 2 different, what are the waves we normally use when we start talking about waves, so in real context? One of them I'm doing right now. Sound, okay, sound's an easy one. So let's put sound over here. And our other one that we would normally be able to see? Light, okay. Okay, so the reason why I've put them into 2 categories is they do 2 different things because they're 2 different types of waves. Now, when we go, I'll start with light. If we go from a less dense, so let's go air, into more dense. So that might be our glass block. So here's my example, air, glass. Okay, the light, so the wave bends. Which way does it bend? Away from the normal or towards the normal? Have a look at the diagram we drew. So it comes into the block. This angle here is quite big and this angle is quite small, so it must have gone towards the normal. Okay, so that's important when we go from air into glass, or when we go the other way, it does the opposite. So in this instance, the wave bends towards, I'm running out of space, normal. Okay. Okay, nice and straightforward. If you can just remember that one, you've got everything else pretty much sussed. Because you'll never guess why I put it in 2 different categories. What do you reckon sound waves do? The opposite. There you go. So I've just given you 4 options that could be occurring. You could be going from a more dense to a less dense. You could be going from a less dense to a more dense. You could be going, it could be a light wave, could be a sound wave. And all I've said is forget all of that, just remember one of them. If you can remember that glass block experiment, that the light's going from a less dense into a more dense, and it will bend towards the normal, everything else you can figure out from that. Does that make sense? Have I lost anyone there? Be honest, ask questions, I can draw it a different way if I need to. And that's OPP, opposite, if you're not sure of my spelling. Okay. Let's talk about ears. Why not? That's what we do every day. Ears. Why are ears important? I hate ears. I just got that from the classroom. Of course we all hate... No, I don't. I like my ears. Okay, first of all, first thing you need to know is what's the frequency range for ears? What can you hear? And you guys are different to me in this respect. There's a couple of really cool tricks we can do with this. I haven't got a demo set up for you. I won't be making anyone cringe today. Because it's a fun demo, because I can make you all like... I can sound like a chalkboard. Very high frequency. Anyone know what the frequencies are? Okay, so really low frequencies, like very, very low. I'm not even getting into the low hundreds of hertz here. I can't talk that deeply, but you've heard people who've got really deep voices, right? Well, actually, it's even deeper than that. You can get down to about 20 hertz, the human ear can hear. Okay, so vibration, so it's vibrating 20 times a second. It's very slow, okay? So we can go from 20 hertz all the way up to, I'm talking a high-pitched voice. I'm probably only about 3,000, 4,000 hertz. Not that high at all. Who's got the highest pitched voice in this room? So we just start bullying each other. Don't do that. I'm just joking. We won't nominate whoever's got the highest pitched voice. If a very high pitched voice, young children in particular, will be about 6,000, 7,000 hertz. So when you start hearing something like that's really annoying, you're up to 7,000, 8,000, 9,000. Eventually, if I use the equipment we have in the lab, I can get to about 20,000. And I'll write 20,000 for a reason. 20,000 hertz. Now, I could also write that as 20 kilohertz. Okay, I've just used the prefix from there. Questions on words?
I don't know what it said with the bending of.
Which on the left-hand side?
Left-hand side.
Okay, less dense to more dense. So the example's air to glass. The wave bends towards the normal. Okay. I know I've sort of started that far too low. I should have started much higher. Okay, so back to ears for a second. Our normal auditory hearing range for human beings, which is a very generalistic term, is 20 hertz to 20,000 hertz. Is that correct though? We'd all be able to hear 20,000 hertz? I'd be able to hear 20,000 hertz? What's the difference between you and me, guy? You and me? You can, yeah. So when I run this experiment for year 7s to year 8s, I will always get kids, some of the kids, not all, some of them will hear up to about 22, 23,000 hertz. I don't hear it much beyond about 18, 19,000 for me now. Now I used to be able to hear much higher frequencies when I was younger. So what's the big difference there? Is age. So as you get older, the bones in your ears, yes, there are bones in your ears, they do get a little bit more calcified, which just means they don't vibrate as easily. Okay, this is why you need to look after your ears. If you listen to very loud music when you're in your youth, you will damage those three bones in your ears, and they will calcify and get scar tissue around them, which means they don't vibrate as well, which means you don't hear as well. Or worse, you get this lovely thing called tinnitus. Anyone ever heard of tinnitus? You might have some older relatives. You want to tell us what they hear?
Like
Constant ringing. Imagine trying to go to sleep at night. You're lying in bed, it's dead silent, and all you can hear is ringing. That is why you have to look after your ears. So you'll see workmen out there side today, we can hear some of them bashing around already. They should be, if they're working with anything loud, wearing ear protection. And it is to protect them from tinnitus later in life. It always annoys me when I see people who aren't, because they have no idea what they set themselves up for. So, that's our auditory range. What gets that information to our brain? I might have given you a hint there. What goes from our ears to our brain? It's not a long tube, I promise. Sends an electrical signal from our ears to our brain. Anyone ever come across someone who has implants that are on the side of their skull, just behind their ears?
Oh, I might have to get them from epilepsy.
No, this isn't for epilepsy. This is for ears.
Oh, but it's something.
Is it similar? Is it for epilepsy? Oh, okay.
I think like my uncle, he's like, it was in like wonking, but he
Okay.
had to have it moved in place.
Oh, okay. Okay. That's not. I don't think that's the same thing, but It could be, for all I know. So the inner ear it's got a thing called the cochlea, and the cochlea is attached to the auditory nerve, and the auditory nerve runs to the brain. So when your ear gets vibrated by sound waves, because they do go in through your ear, and the sound waves rattle the bones inside, and that generates an electrical signal that goes to the brain. Sometimes people don't either born without a cochlea, or a cochlea is faulty, or it gets broken. So I used to teach a girl at one of my schools many years ago. She would probably have just done her A-levels by now, but she was in year 7 when I first met her. And she was born without cochleas that were fully formed. They didn't work at all. She's effectively deaf. And all of a sudden, there's technology's improved, and they're able to put what's called a cochlear implant, which takes the path from the ear to the cochlea and the cochlea to the brain, takes over that spot. And she went from not being able to hear to having really, really good hearing. I had to wear a special microphone so when I was just talking like I am now, she would be able to hear that clearer. I had to also remember to take the microphone off, otherwise she'd hear every conversation I ever had. But she went from being a fairly average student who really struggled, not surprisingly not being able to hear, to being she was at top grammar school getting top results. So it was really holding her back, and technology thankfully moved fast enough for her that she could get the benefit out of it. But the ears are fairly sensitive things, but there's a lot of technology. So if you ever see somebody they look like they're like little boxes, not matchboxes, that's too big. Maybe like a quarter of a matchbox, and they are, I think, glued, I might be wrong, onto the skin, and that's what they're for. And you don't need to shout at them, they can hear you just fine. They do struggle with certain frequencies, so when we're talking about those high-pitched noises, I would never be able to put that on in the classroom with her in there. It would be like torturing her, okay, because it would do strange things, nerve signals to the brain. Right, so that's ears bending. Let's go and have a quick look at ultrasound. So let's put on ultrasound, and we'll put on infrasound as well. Okay, tell me what you know about ultrasound. Anything at all? Dolphins, good. And I'll put dolphins, and we'll add something to that in a second. Go. Yep, we can use it for medical imaging. And the example, if you didn't hear it through the computer from the classroom, was pregnant women have ultrasounds. Not just pregnant women, it's very non-invasive. So if you have an issue with your spleen or with your liver, they can do an ultrasound rather than having to do anything more invasive. So anyone can have an ultrasound. Anything else we know about ultrasounds? So I've had dolphins. Anyone know what dolphins use it for? That's part of it, but not the only part. That's not actually even the main part.
Don't they use it for navigation?
They sort of. Again, they can find things in murky water using it. What do dolphins need to eat? What do they eat? This isn't a trick question. Fish. How do they find the fish? They've got eyesight, yes, but they use their echolocation is the word I was looking for. Go on, speak up. So they do make both ultrasound and what we can hear, clicking noises for communication. But the echolocation is the main part of what they use ultrasound for. What other animals do we have that use it? Bats? Oh, whales. This is where I go, dun dun, good answer, but wrong. But we'll come back to that in a second, because your answer will fit on the board somewhere else very well. So dolphins, bats, usually anything that you can't hear that's flying around in the dark is using echolocation. What's the difference between a bat and a dolphin? Don't say bird and fish.
Fly.
They fly. How about how fast they're moving? How fast does a bat move? Really fast. So Mr. Mumford, you know Mr. Mumford? Dan DT? Design Technology? Yeah, me and Mr. Mumford sitting in a tent on Jig of Edinburgh in the big gazebo thing, waiting for some kids to come in, and it's dusk. It's just starting to get dark, and the bugs are starting to come out. So we're sitting there going, oh, we should probably do the fly screen up on this big gazebo thing. Oh, I can't be bothered. We'll just wait a little bit longer, then we'll pack up. While we're sitting there, so it was just chatting around, a bat flew around the gazebo. Now, all we saw was a shadow, and then flew straight out. happened within half a second. It's that quick. And it'd come in to eat all the bugs that were in the gazebo. Now, it's using echolocation to do that, so you can imagine the speed that it's working at, whereas a dolphin probably has a little bit more time to think. And that's why a bat can see very, very small things. A dolphin doesn't need to see things that small. It's not going to eat things that are tiny, it's going to eat things that are a bit bigger. That makes sense? So, still echolocation. What else uses echolocation? What about humans? How do we use echolocation? Yes. Yes, that's a good connection there. I'll give you a hint. Con sonar. No one's watched any submarine movies. Ah, right. Hunt for October needs to be watched by all of you. No, I'm joking. I can't make you watch that. Sonar on submarines and on ships. So warships use it to find other ships. Submarines do it to make sure they don't run into anything. Also tracking other ships and the bottom of the ocean, whales, etc. So I'm going to also put in, just so we don't, we've got medical imaging and we've got sonar. Okay. Right, infrasound. Ultrasound, really high frequency noises. Anything above 20 kilohertz is considered ultrasound. It goes way up into, I'm going to quote this wrong, but I'm going to go 40 megahertz. So it's huge. Okay, way past us being able to hear. Infrasound. If we've got ultrasound going up, what do we think infrasound might be? Going down, smaller than 20 hertz. And guess which animals communicate in infrasound? Whales! There you go, I told you it was going to come in. Whales. Okay, which is one of the reasons why whales can communicate so far around the world. Okay, when a whale is talking to another whale, they can be hundreds of kilometers apart. It's quite something else to think that the Earth is curved and they're at different points on the Earth, and there's lots of bits between them, but that sound is trouble because it's low frequency. Okay, let's just check I haven't missed anything massive there. Primary and secondary waves. We've done a little bit of talk about earthquakes, haven't we? Okay, so what I'll do is I will write earthquakes up here because I'm going to cheat. I'm going to borrow something I've done earlier. Earthquakes. Anyone ever experienced an earthquake? Anyone? I've only been through one that was very small. Okay, so earthquakes are made up of two. Okay, we have a primary wave and a secondary wave. Primary and secondary. I'm just going to abbreviate them because I don't quite have the space. And the primary wave is longitudinal. So if you can imagine, I'm not actually going to do this, but I walked up and I tapped on Will's desk here, like this. Bang. Okay, what's the desk going to do? Which way is it going to go? Shake, but which way? Yeah, that way. The wave's going to travel longitudinally through all the particles in this table. Are going to go very quickly, but all the way through the table. We're happy with that? That's the primary wave. Doesn't do too much damage. Starts to shake things, probably scares people more than anything. So that is, oh, where am I? Can't draw on that screen. That is a longitudinal wave. The second part of an earthquake, because that one travels quite quickly. That one, depending how far away you are from the epicenter, you'll feel that one first, and then there'll be a gap. And then the second wave arrives. Now the first wave, the particles will work. Imagine if I could grab the particles at the end of the table, and I could grab them. Are you touching the table? So I could grab them and I could shake them. Okay, like a rug. Shaking a rug out, and all the particles along the table do that. It's a transverse wave. And for an earthquake's point of view, that second wave does all the damage. If you can imagine you were sitting on a building, was sitting on particles doing that, that's where it starts to shake the building in all sorts of lovely directions. And if you build anything in San Francisco, for example, which is in a huge earthquake zone on the, I can't remember the name of the fault line, it's avoiding me now, you have to build it so it can withstand huge earthquakes, so it can absorb all that energy for a short period of time. So those are our secondary, and they are transverse waves. Guys, that is a lot of information on P4. I won't start on P5 now because we've only got about 6 or 7 minutes left. I'm going to stop the video and then we'll chat through any questions you might have.